Good afternoon, everybody, and welcome to this session on building resilient event-driven architectures on AWS. My name is Himal. I'm part of the solution architecture team, and I work very closely with travel and hospitality customers who are building resilient architectures on AWS. With me, I have Izil, who's a principal solution architect, and Vinay, who's a principal architect at United Airlines. By the end of this presentation, you will learn why are event-driven architectures becoming so popular and why are customers adopting them. We're going to talk about a couple of patterns around governance and resiliency. Then Izil is going to come in and talk about data protection within these architectures. And in the end, Vinay is going to come and tell us about the United story where they are moving from a mainframe system to an event-based system. There's a lot to cover. Let's dive in. To answer the question on why event-driven architectures are becoming so popular and why are customers adopting that, first we got to understand the business requirements. And most of the time, these discussions starts around application modernization. As a solution architect, I talk to many customers, and the first thing we usually start talking about is how do I break my monolith into a smaller microservice-based application. But every system is built to meet business requirement. Now, as our business partners are telling us to go faster, be more reliable, less defects, and be more cost-effective. This is not actually a vision or a future requirement. This is something that is happening today, as our business partners are giving that as a requirement today. So every application owner has to actually have that, need to have the application owner. These are hard requirements in this current competitive landscape. So most of the conversation is starting around how do I decompose my monolith into microservices. Now there are many different ways of decomposing your monolith. Decomposition is happening using business domains, subdomains, and using strangler pattern. Now a lot of these decomposition patterns are actually well suited for a greenfield based project. But if you have an existing system which you need to modernize and move to AWS, strangler pattern is becoming extremely popular. Now, strangler pattern is where you will extract a particular functionality and modernize it into a system which is on AWS. The older the monolith supports the new modernized application, and at some point of time the monolith will be completely decommissioned. So what are the advantages of these modernized applications? First is when they are converted into microservices, they are small and specialized so that they can scale to millions of users. They can be deployed independently. Now, and individual teams can have frequent deployments for these microservices. Third, they are typically modeled around business domain and exposed by an endpoint, which every other application can interact to. And fourth, you have separate code bases, separate business teams, so there is less dependency, which increases resiliency. So let's talk about event-driven architectures. So microservices focuses on decomposing applications and moving them into smaller unit. The common way of communicating between these microservices is an API, which is typically a REST architecture pattern. So REST API are exposed by the microservices, and they support standard HTTP methods, which makes them flexible, scalable, and discoverable. Now, REST API is a good way to expose your microservice, but the challenge is that when you actually make a call to the API, the microservice is actually waiting for a response back. Now, if decoupling and loosely coupling is important for you, and you have applications which is going to scale up, or their scale is unpredictable, another way of doing this is having a message broker or asynchronous messaging in between. Asynchronous messages is fundamental approach for integrating multiple different loosely coupled microservices that can actually evolve, scale independently. Now, here's the definition of an event-driven architecture, which focuses on a few things. One is it's an architecture pattern. Second, there are loosely coupled systems. And third, they emit and respond and process events. Events can be as simple as a change in state within the application, or a business event like an order created in your order management system. Now, a principal at AWS summarized this very well. He said, if any application which is modern, cloud native, distributed, and if does not have a messaging layer in between, well, that's probably a bug, right? So let's dive into what these event-based systems are, and then we look at a couple of other patterns. At the core of it, event-driven architectures are fairly simple. There are producers and consumers. They will emit and consume events. Then these can be microservices, on-premise systems, mainframe systems, even middleware systems. And in the middle, which processes, stores, routes these events, are message brokers. Now, there are a few important patterns we need to understand. One is there are event stores, which acts like buffers for your decoupled application. An event comes in, a consumer actually picks up that event, processes it, and the event is deleted. Second, there are pub-sub patterns, or publisher and subscriber pattern, where publishers will publish these events. They'll be stored, and multiple subscribers can consume them. Third is event routers, which provides additional functionalities like filtering and routing capabilities, most typically used in fan-out patterns. Event-driven architectures are becoming more and more accessible. In AWS, we have the AWS messaging services can be broken down into two things. One, AWS native services like Amazon SQS, SNS, and EventBridge. They are adopted by born-in-the-cloud customers, typically adopted by born-in-the-cloud customers, and SaaS providers. Enterprises are adopting what AWS provides as a managed open source services, because they have native integration into their existing systems, like Amazon MQ, which has Apache MQ and RabbitMQ, and Amazon managed streaming service for Kafka. In today's presentation, I'm going to focus on managed streaming service for Kafka in the examples that we're going to talk about. Now let's start with the governance architecture. So microservices and event-driven architectures provides you a good paradigm for managing your applications. Microservices focuses on individual application components, whereas event-driven architectures will talk about the communication between them. Now, many customers ask us, what are the fundamental components that is required for providing the governance for such architectures. Fundamental architectures in this case means infrastructure choices, access controls, change management, blast radius, etc. Now, most customers start here. You have one AWS account. You have applications moving to AWS. They are all sitting in that one AWS account. They are exposed via an API or a messaging architecture. You have events coming in from your on-premise systems and also integrations into your data lake, into your machine learning services. Now, this is a good architecture. This is a good start because everything is sitting in the same AWS account. Integration becomes easier. You can talk to every domain can talk to each other fairly seamlessly. But how do we improve this architecture? Many customers are adopting what is called as a micro account architectures. Now, in this, every application team will get its own AWS account. They will connect to either a central Kafka cluster, which is part of their own domain architecture, or an enterprise Kafka cluster where every application is communicating to each other. Now, there are certain advantages in this architecture. One, because we are putting all these applications in a separate AWS account, that immediately increases the security, security because of the account boundary, and it reduces blast radius. Now, there are a few other advantages. Will be resource isolation, access management, better access management. Every application team has its own AWS account, so there is more flexibility because they can now experiment within that AWS account better. And lastly, you have full cost visibility as part of this architecture. Let's double click on the access management a little bit. Now, when you implement, when you install the MSK cluster, you will be asked to create a cluster policy, which is nothing but a resource policy that is implemented within MSK. This is a way to govern on who can connect to this Kafka cluster. This on the client side, you also have a way to connect to connect to that Kafka cluster by implementing a resource policy at the endpoint. So the client will also be connecting, will have an authorization at its end to connect to a central Kafka cluster. Now, this MSK came out with a capability called multi-VPC private connectivity that enables this particular architecture. Now remember, this because you're using private link to connect to the central Kafka cluster, the traffic is always sitting inside Amazon backbone. Now, so once your applications have moved to AWS, resiliency, it becomes an important topic. As practitioners, business resiliency assessment has always been a conversation for us. Now, many organizations implement event-driven architectures using AWS serverless and managed services technology. Now, serverless and managed services technology from AWS are regional services, which means you get a unified experience and you don't have to worry about availability zone implementation. So all that heavy lifting is done by AWS behind the scenes. Now, but in some cases, customers have stringent RTO requirements. So how do we actually extend the event-driven architecture into a cross-region, multi-region architecture? Let's dive into that. Now, here, as we spoke, you have multiple application teams building their microservices, their modular architectures on AWS in multiple different AWS accounts. They are all communicating to the message broker. Your customers are consuming these services publicly via Route 53. Now, every application team will have a DR policy. Typically, the DR policy can be as simple as backing up your application data, or we have seen customers actually implement resources. The application team deploy the resources in a different region. and enabling replication. So let's dive into this architecture on how this can be achieved. So when an actual failure happens in one of the regions, if there is a regional impairment or a component level failure, you can quickly switch over traffic to the secondary region, which will drastically reduce the RTO. Let's dive in. So MSK, again, came out with a capability called MSK Replicator, which gives you the capability to replicate traffic, your events from one region to another. The MSK Replicator supports active-active and active-passive deployment. In fact, MSK Replicator not just replicates traffic to another region, you can also use that to replicate in the same region too. So in this case, the producers are producing the events to the MSK layer, which is being replicated to the secondary region. In case of a failure, in this case, for example, I'm showing that the MSK cluster has failed. Maybe you ran out of storage and you need some time to fail over the application to recover the MSK cluster. To reduce the RTO, what the producers can start producing messages to the second MSK cluster in another region, and consumers can be pointed directly to the secondary region. Consumers will get their secrets from the secret manager and connect to the secondary MSK cluster. One thing is important to understand is sometimes you need to also take care of the consumer lag. That in case some consumers are consuming from a different region or maybe even on-premise systems. There are a few other considerations. I think the biggest point there is have a robust observability and health check practice. The second is failover process for automation. We have seen advantages where customers fully automate their failover process using AWS serverless services like step functions and Lambda. So patterns like these can be implemented for faster failover and reduced RTO. Now, let me call upon Izil on stage to talk about data protection for event-driven architectures.
All right. So data protection should be part of any system that we're going to build or augment, modernize. But today we're going to discuss a bit more about data protection for event-driven architecture. And today I'm going to call that EDA. So first we're going to go back a bit to the basic characteristics of EDA-based systems. So we already see with ML there are already multiple components that will transmit information from one component to another. So basically, we have event emitters. So they are event producers that are sending events to our system. We're going to have at the downstream of our system event consumer. So they can be different type of computes that will consume in events, and they may run some business logic, augment the data, and ultimately send the event to be stored in different type of storage. That could be your database. In between, we have event channels. So these are the services that we've just seen, some of them, that can be used to reroute a message, fanning out a message to different subsystem of line of businesses that we may have. We can apply different rules for filtering those messages. And all of this will be communicating on top of a network layer. So these are the basic characteristics of the new system that we're building or modernizing. In short, the big difference between this and most classical systems is that there's a lot more data in movement. Okay, there are data moving or events moving from one component to another. There are detached components, but there's also a lot of movement in between different locations. So those locations could be your legacy application or your mainframe that is still sitting in your data center that would transmit information to the cloud. And within the cloud, then you may have information that is moving from one EZ to another, and possibly from one AWS region to another region. And ultimately, we're probably going to have events that are moving back from the cloud to your data center to be stored in your mainframe for data consistency reason. So there's a lot of data in movement, and all this over different network layer. So these are the foundation of EDA. Now, you've probably seen this slide many times in previous reInvent sessions, Reinforce sessions, our documentation. So this is the shared responsibility model. The reason we're having this slide again today, it's because most of the services or component that you're going to use to build your EDA systems, they're cloud-native services or managed open source services. So they tend to be on the right side of this graph. So meaning they are abstract services. Yet there are still a section, the section in purple, that is your responsibility as a customer, and you need to protect your own customer data, and that will also include client-side encryption. Yet that doesn't mean that you can turn just a blind eye on the green section of this graph. So the green section, this is our responsibility at AWS. But still, if we take, for example, server-side encryption, which is just underneath client-side encryption on the right side, this is something that we handle for managed services and cloud-native services, but you still have to configure it and possibly enable it if it's optional for the service. Now, we have a few EDA data protection best practices. So since we're moving a lot of information, we want to make sure that we're only moving what is absolutely needed to act on the data. So I'm not necessarily talking about the quantity of information as a whole, but if we take a single event that you're transmitting, it's probably an object that has a lot of attributes and parameters. So you don't want to include attributes that you don't need to act on this event. The reason is you cannot leak information that you do not have, basically. So we're not talking here about major mistake in leaking data on the internet. Here we're talking about basic mistakes. For example, you're enabling full debug mode in one of your containers, which is basically a middleware in your system, and you may end up with those events in your logs. So if those events have sensitive information and they're not pre-encrypted, you're going to find it in your logs, and we could consider it as a data leak. Also, keep in mind there's other parts of your message that may be metadata. There could be a context around it. It could be your topic name or your bus name. So you want to reduce that to the absolute minimum and make sure that you do not have sensitive information in those fields. There could be a scenario where the system that is sending you events is not removing this information that you do not need. So in this case, in your architecture, what you want to do is simply, as quick as possible in your architecture, to add a step where you clean out this information that you do not need, basically just filter it and remove it. And third, you always use encryption. And this is where we're going to focus the rest of this presentation. Now, basic step one, encryption in transit. So basically, we just want to make sure that every time we send information to our system, we're using a secure protocol. This is fine. But we also want to make sure that when our EDA components are communicating to downstream system, they're doing the same, using secure protocol. Now, there's also encryption at rest. Now, we don't want to make the mistake to just think about the end state of our events. So in the last step, which is our storage. So it's not just about encrypting the storage behind our database here. So each of our components in EDA may store events for a certain period of time. So I could have an event router, could have a bus. It may store an event just for a couple of milliseconds. But those services, some of those services, they allow you to store events for days and weeks. So this is why you want to make sure that you enable encryption if it's not enabled by default in those components. And the third one is client-side encryption. Now, in this context, we could call it producer-side encryption. So any system that is emitting an event should pre-encrypt the object or the payload that you're sending. But we'll see what does it mean and how does it apply or affect our EDA system. Now, just before we continue, I just want to do a quick recap on AWS KMS, which stands for Key Management Service. Basically, this is a managed service that allows you to create, manage, and control cryptographic keys in AWS. So most of our services that encrypt information will integrate with KMS. And you can use the API behind it to create and manage those keys. Now, it can do a lot more than that, but for today, this basic description is enough to understand the rest. Our goal today is to make it easier for you and your developers to implement encryption, leveraging KMS, without over-complexifying our architecture. We already saw a few of those components. These are cloud-native services, or they can be managed open-source services. Those services, they can help you with queuing, streaming, topics. They can be a broker, a bus. But what is important is that, first, we always recommend that you're using the secure endpoint, so with using TLS 1.2 minimum. Some of those services will enforce it. For others, it's optional. But it's also important that you make sure that if those systems are sending information to external endpoints, that they also use a secure protocol. Now, as for server-side encryption or encryption at rest, some of those services, it's optional. For others, Inforce, but they all integrate with KMS. Now, one thing that you have to think of is that there's a few distinctions in some of those services. So just give you an example. With Amazon MSK, which is managed Kafka, application at rest is enabled by default, but it can be deactivated. So you want to make sure you have governance in place and guardrails to avoid it being deactivated. For Amazon MQ, which is our service for managed ActiveMQ and RabbitMQ, there's a few distinctions here. So with ActiveMQ, encryption at rest and inter-node communication within your cluster is enforced. It's always using TLS. But as for Amazon MQ, RabbitMQ, the inter-node communication does not yet support encryption. So this distinction is very important. Yet for RabbitMQ, your cluster will be deployed within your own VPC, so traffic will only be in your VPC. And for region-to-region communication within the cloud or in between AWS data centers, traffic is encrypted at the physical layer. But these distinctions are important, and this is why that if you're going to use those services in your architecture, you should take the time to really look at the documentation carefully, make sure that you're probably setting up encryption. Now we're going to have a look at a few examples. So here I have a very simplified EMR system, which stands for electronic medical record. So we have, for example, physician that enter patient information. We have our EMR system receiving that. It sends this information to a topic, and the topic will fan out to different queues because we have different systems that may react depending what the physician is trying to achieve. So here I have a billing system, I have a scheduling system, and a prescription system. Now, very basic, make sure that I use HTTPS everywhere, end-to-end. This is fine, easy to do. But I want to leverage encrypted queue, which is possible with Amazon SQS. Now, these two services, Amazon SNS that I'm using for my topic and Amazon SQS for my queues, they integrate together and they can leverage encrypted queue if I both configure them to use KMS. So basically, when my EMR system will send an event to SNS, it will be transparently encrypted. And then when my billing system will consume an event, SQS was transparently decrypted. So that's my basic architecture. We're going to go back to it later. This is a very simple example of client-side encryption. So I have an object on the left. On the right, I have field-level encryption, meaning that I still see the attributes, but my properties are encrypted. This is just an example of my object. Now, there's a few things to consider when you mix client-side encryption and EDA system. You have different choices. You could decide to encrypt the entire payload or your entire object, or you may decide to do field-level encryption like we just saw in the previous slide. So there are pros and cons with both. So if we do payload-side encryption, we may reduce encryption overhead. And when I say overhead, I'm not necessarily talking about heavy compute cycle to encrypt it, but message side, when I consider my entire message is encrypted. When using envelope encryption and digital signature, you multiply that by each of the attributes that you may encrypt. So this is why you're reducing overhead by encrypting the entire payload. Now, this works very well with the point-to-point system, where I have a system sending information to another one. So one is encrypting and the other one is decrypting. But in the EDA system, it's not that great, because we have services and components that are there to read the events and maybe apply filtering rules, routing rules, or basically, depending on our rules, sending the events to multiple end consumers. Now, if I encrypt my entire payload or object, sadly, my EDA components are unable to do that. So there's pros and cons. So I may need access to some of the fields, but not necessarily all of the fields. And again, like I mentioned earlier, you want to avoid adding sensitive information to metadata, context, bus, or topic names. I'm going back to my previous example. So here I have an object. It's about a patient. So I have his name, I have his social security number, I have another attribute which is called keywords. On the right, I have the same object, but now I'm doing selective field encryption. Basically, I identify attributes that contain sensitive information. I apply client-side encryption, but I'm going to keep an object here. It's called keywords. So at least I can use this as a reference or as a context to apply some rules if I need to reroute the message in my EDA system. Now, to do all this as a developer, okay, we want to simplify our life and develop faster and modernize faster. So we offer AWS Encryption SDK. This is open source, support multiple languages. It's something you can import in your middleware backend system, but also in a static front-end application or even your browser. It interacts with KMS, support key rings and multi-region keys. It would make the life of your developers much easier. It will be faster to implement this inside your application. It's using envelope encryption, and it solves two challenges, which is, first one, we already said, data protection by encrypting your information, but also data integrity, because it adds a digital signature in the envelope encryption, making sure that we have the same information that we sent. So I'm going to go back to my EMR system, still using encrypted queues and secure protocol. But now I'm importing the SDK in my EMR middleware. I'm using field-level encryption. Very easy to do. So I have end-to-end encryption on those fields. I still have context that is decrypted to apply rules. And then I can import my SDK and give access to the keys only to the services and microservices downstream that actually need to act on the data. If they don't need to act the data, they don't need to decrypt it. I could go and store it directly like that. But if they need to augment the data, modify it, then I can give access to the key and import the SDK to do that work. Now, this is the third variation. It's almost the same, but the difference is that now I'm importing the SDK in a static UI. So that could be a React.js application, could be an in-browser application, but basically I have my physician sitting at the clinic, is using his local application, and we're going to pre-encrypt the field before we even send them to our EMR system. So before we send them to maybe the public internet, we're still going to use HTTPS, but we're going to do client-side encryption on the local machine first. Now, in this example, maybe I have hundreds of clinics around the country, possibly 1,000+ physicians doing this type of work. They're probably using legacy application, the same application they've been using for years. And here we're modernizing our EMR system, so we have a brand new system in the cloud, but it's probably very difficult or almost impossible to have access to those clients and modify them. So there is a lesser known feature of CloudFront that is called field level encryption. So CloudFront support that. So I could front my EMR system with CloudFront, activate field level encryption. I need to know the fields in advance, but at least I can say when you see the events of this type and it has those fields, apply field level encryption automatically at the edge. Behind the scene, the service does use the encryption SDK. It's going to use a public key, and then the event will exit CloudFront and will be sent to my EMR system, stay encrypted, and then I can give access to the private key to my microservice that need access to those fields. All I need to do, again, is to include the SDK and do decryption. Now, there are some limitations. You need to know the fields in advance. So you need to know how the system works, the exact events, and there are limitations in the number of fields you can apply that. So if this is too limiting for your application, we don't see it in the graph, in the diagram, but you can use Lambda at edge, which is basically a Lambda function that allows you to put logic that integrates directly with CloudFront. So CloudFront will receive the event, pass the event to your Lambda function. Inside of it, you can import the SDK, apply field level encryption in your selected fields, and will give the event back to CloudFront, and CloudFront will pass it on to your downstream system. So these are easy ways to apply client-side or producer-side encryption. And with that, I will pass it down to United Airlines, and we're going to see a real example of how they're using EDA to actually modernize their mainframe in production.
Thank you. Good afternoon, everyone. I am excited and happy to be here. My name is Vinay Patil from United Airlines. I'm responsible for architecture of PSS system applications. Today, I'm here to share our transformation experience using event-driven architecture that has set up us for success. During pandemic, we found creative ways to help our customers. And we launched United Next. United Next involves buying more than 700 aircrafts, and these creates a lot of volume and traffic for our digital systems. Also, just last month, during the Memorial Day weekend, more than 3 million passengers took United flight, setting a record for a travel period air travel. To support this, a lot of transformation is happening at United across the digital systems. United loves to own its destiny. What it means is, during conversations, when this topic comes up, whether to build or buy, we don't hesitate to build the software if the capability does not exist in the market. A typical trait of a software company. Our success so far is built upon mainframe systems, which is a backbone of our operations. This system just works flawlessly. They provide 99.98% resiliency and availability. However, over a period of time, it has grown in terms of complexity as we are incrementally building capabilities on top of it. And this system has, this is to support this growth from the United Next program. We have very limited talent available in the market to work on these mainframe projects, and this hinders our pace of innovation. Just to give you an example, if you have to trace a transaction for a customer end-to-end during his journey, it involves significant amount of work in the PSS system, whereas the agents who are serving our customers need this information in real time. And this is the reason we have to transform the PSS system. When you are making a reservation online, at the end of the transaction, your reservation is created in PSS system. That's where it is created, processed, and served. PSS system is also responsible for departure control. What it means is all the airport operations, be it check-in, boarding, accepting your baggage, and so on and so forth, are handled by the departure control system. In addition, it has an integration layer which integrates with all our internal applications as well as external. Internal may be customer-facing, our on-premise applications, and on-prem, and in cloud, because they are also going through transformation. It also integrates with external systems, other airlines, our partners, and agencies. The complexity surrounding this mainframe system requires careful examination. We follow, this is a kind of exercise of event storming in a typical EDA system. We follow a three-step process. The first step is really to document your current functionality or your current state. Then we go through an exhaustive analysis of all the dependencies between the components, functions, and things like that. This is a very deep level analysis required in the mainframe system. And we have some in-house tools built in to perform this analysis, because we repeat these three steps every time we have to rebuild this, every time we have to transform our capability. Also, we follow, for this decomposition process, we follow a methodology, crawl, walk, and run. Crawl involves understanding what the complexities are in this transformation journey for us. It's a long journey, so in the crawl phase, we also identify what we need from a process perspective, what tools we need, and how to be successful. In the walk phase, we have some tools and templates created, which helps us accelerate. Right now, we are in the walk phase. When you shop online for any product, what you do is you search for a product, you make a purchase, and then the order is created, right? And the order is fulfilled. This is a very customer-centric approach, which we all are used to on an e-commerce platform, and it is handled by an order management system. We are pivoting towards it because it's customer-centric. All our customer-facing applications have already pivoted, but in the back end, in the PSS system, we are still around capabilities. The difference shows up when you are looking up for your previous order purchase, you enter an order number and you look up based on that. Whereas when you are at the airport, when you are trying to check in, you enter that confirmation number and the name. So that's the key difference. What it does, if we pivot towards a domain-based approach, similar to order management system, it helps us leverage all the capabilities which have been created across the multiple industries. And it helps us lead in the transformation journey for the industry. As we are redefining our business, it helps us remain compliant with the rest of the industry, at the same time not constrained by the technology what we have currently. To support the complexity of the mainframe, we are using a strangler pattern. Himal talked about the strangler fig pattern. There are 3 phases to it, 3 stages of it. We are going to stay in the coexist phase for a long period of time, because as we are strangling and we are developing new capabilities in the new system, we still have to integrate with our partners who may not have been there. So we will be integrating with those systems as well, and that's where we'll stay in a coexisting for a long period of time. Because think about it, internally we are talking order, but externally we are still talking reservation, PNR, and things like that. As we are strangling and building these capabilities into new PSS system, how do we eliminate? Well, a lot of you must have seen when you are at the airport, whether you are at the baggage acceptance counter or at the gate, there is a green screen that shows up. And some of our agents are still using that green screen. It is a direct interface into our mainframe system. So as we are strangling the capabilities from mainframe and putting those into a new system, we decommission some of the commands which are available to the agents so that they can migrate to the new capabilities. Also, at United, we have been using message-oriented architecture for a long period of time. That makes it a logical transition for us to an event-based architecture. These are some of the key requirements we got during the crawl phase when we started on this transformation journey. 1.7 million flights. Anytime you book a ticket in advance, you are able to book about a year in advance a ticket. What that means is, in our system, we have 1.7 million flights at any given day. When you are selecting a seat, you navigate to a seat map, which shows you in real time what the current seat layout is, who has taken a seat. That creates a request, and we are getting 8.5 million daily seat map views. Now, if you all have traveled during last 1 year with United, you have been served by these transformed capabilities. So as I said, during the crawl phase, we learned a lot. And all these learnings we have captured as part of our template architecture. We call it as reference architecture. This helps us move fast during the walk phase as we are transforming more and more capabilities. When we decide to move a certain capability based on our decomposition pattern, we have to bring up a stack, right? An infrastructure stack. Every application, if we do that, it's not really sustainable. So we have taken a platform-centric approach where my friend referred earlier around micro-account architecture, whereas we set up a micro-account with a shared architecture, shared infrastructure, for example, be it messaging, be it logging, or any other shared services which we need for the application. Once it's part of our platform, it can be used by multiple applications which are part of the domain. Let me double-click into certain aspects of this reference architecture. all of us shop during the Black Friday event, and it creates a lot of stress on the e-commerce platform. For us at United, it is, in certain cases, it's unpredictable, like a weather event, or it's a holiday period travel. We get a lot of traffic and stress. During this period, we have to ensure that any kind of disruption or traffic that needs to be handled scales. We are using EKS and ECS to manage our compute workload, and we are using purpose-built databases to scale the traffic. In addition, we are also using service mesh to make sure that we have zero trust policies set up between the service-to-service communication. To get visibility for our ops team into how the system is performing, we are using AWS native services like CloudWatch and CloudTrail. These services stream all the infrastructure and application logs into Datadog, which provides us insights into real time, and Big Panda gives us further insights. It avoids all the noise and gives us insights so that tickets can be created and our ops team can act upon it. Security is an inherent part of our design. We are using Secrets Manager to track all our secrets, and for data encryption, we are using Key Management Service to maintain the keys, and Oracle Access Manager for authentication and authorization. As we are transforming capabilities from our mainframe system to the new application, all the integration of the customer-facing applications need to move on to the new capabilities. To make sure we have a proper integration, we are using API Gateway for seamless transition. And also, it gives us ability to route the traffic correctly to the new capabilities and give them an early preview into the new services or the new APIs by creating some mock API services. And lastly, loose coupling. We are using Amazon MSK and Solace for our message broker, which allows communication between the services in the application and also across the applications in the domains, across different domains. It also helps us to send all the events downstream to our data lake. As we have set up this reference architecture as a template, we also found out multiple patterns for the event-driven architecture. Some of those are standard, and some we have created so that we can use it for our future applications. As I said earlier, when we are going to coexist for a long period of time, when you create a reservation, in this scenario, a reservation is created and it is stored and processed in the mainframe system. The mainframe system sends messages to our new system, transform systems. These messages creates the order, and that order is basically maintained in the new system. Once we have all the messages coming into the transform systems, this gives us insight into what kind of traffic we are going to see in the transform system. These different type of events could be, the first one is order event. When you create a reservation, an order is created in a new system, and any kind of updates, you will see that in the order system. In addition, any life cycle events, for example, after fulfilling your reservation, the reservation is closed, a corresponding event is created in the new system to close the order. And lastly, when you check in at the airport counter, a check-in event is created, which is again updated in the order. It provides us insights, as I said, in the to understand the stability of our new system as we enable the traffic and when the traffic is reversed. Right? So when the traffic is reversed, the same order, your reservation will be created in the new system, and the order will ultimately create a reservation in the back end because we have to stay compatible with the industry. So we have to event out it as an reservation. This is a pops-up pattern. Here, as you can notice, the events which I talked about on the left, they are streamed to our downstream systems, be it a baggage control system or the events to a server customer. Now, as I mentioned earlier, our agents are looking for information in real time, right? What changes are happening to the reservation. Once these events are evented out from our new system, it is enabling us to stream these events to Amazon Bedrock, from where the events, the insights are available to the agents in real time. This is what is enabling it. When you select a seat in your app, it's persisted in the database, and then on persisting in your database, we event it out and maintain it in an exception database. Eventually, when the transaction completes in the legacy system, it is again streamed, and the similar event is streamed and it's maintained in the exception database. Periodically, we run a process to ensure that the data integrity is available between both the systems. If it is not, we run a reconciliation process to ensure that the data is consistent across both the systems. This is a nightmare if you think about it, having a two system of record at the same time. These patterns enable us to keep that data integrity. Context injection. This is another pattern which we have identified. This helps us to provide context to our downstream systems when there is no context coming in. It enables to handle any race condition and any IROPS events, the weather events which I talked about earlier. This is a failure pattern wherein, say, there is a messaging failure or a database failure. In that case, the producer with the circuit breaker identifies the failure early on and turns off the traffic, and it raises an alarm so that the traffic can be routed to the secondary region. We have an orchestrated process for our disaster recovery. This ensures that there is a minimal data loss. The key thing here is we ensure that the services are brought down and started up in a specific sequence. These are some set of guiding principles which we have identified both during our crawl and walk phase, and it helps the applications which are being developed currently to make sure that they are resilient and they are following the EDA patterns. So to summarize, our event-driven architecture is the key enabler for resilient PSS systems, and the data generated from the PSS system is fueling innovative capabilities, enhancing your travel experience. Thank you.